Good evening, lads. Tonight, I'm here at the outskirts of the luscious forest of Metro Manila to find the Philippine Cobra. Oh my gosh, did you see that?
No.
Well, play it back. Check the replay. But you know what? Come closer, come closer. Found something in it. Found
Is that
something.
the Philippine cobra?
No, it's even better. It's the seed of a Benguet pine, also known as the Pinus cassia. You know, the cool thing about this seed is its ability to auto-gyrate. Come closer, zoom in. See, this seed, as it falls, it generates enough lift to rotate and traverse further distances. Ain't that cool? Let me show you it's done. Oh, ain't that a beauty? Ain't that pretty? Now, what I want you to do is as the seed's falling, take a look at it from down under. Yeah. Pause. Multiply the seed 3 times. Now what you got there? Looks awfully familiar. It looks like a wind turbine.
My friend, if you're wondering what a wind turbine is, let me put it simply. Here is an electric fan. We give it electricity, it spins, and we get wind. But let's reverse it. We give it wind so that it spins, and then we get electricity. Is that possible? Well, it is, with the help of wind turbines. In fact, we have a lot of them in our country. The ones that look like windmills are called horizontal axis wind turbines, or HOTS for short. And most of them are very big. But for today's video, or study, we'll focus on the small ones. Problem with them? They're not that efficient yet. Some studies used other auto-gyrating seeds to improve their efficiency, and they were successful in doing so. But until now, no one has used Benguet pine seeds as an inspiration, which brings us to our study entitled Development of a Benguet pine Pinus cassia seed-inspired horizontal axis wind turbine blade.
After procuring the seeds, we investigated some of their properties. Their length and width were measured, then the presence of a curvature was determined. We then proceeded to conduct a test where we dropped each seed and determined their fall times. The one with the highest average was used as a basis for the seed-inspired blade. This seed was then 3D scanned to be accurately measured. Using a modeling software, we followed its width and curvature with a set airfoil as a cross-section. With this, the seed-inspired blade was assigned, with a blade length of 13.6 centimeters. The control blade was also modeled with the same blade length as a seed-inspired for the swept area to be constant. Both were 3D printed with roots for them to be mounted to a wind turbine kit's hub. During the testing, both blades underwent varying wind speeds, 9, 10.5, 11 meters per second, and varying angles of attacks, 15, 20, and 25 degrees. We then recorded its voltage output every second to calculate the power output. The blades were also simulated in a C-shaped domain to get the lift and drag coefficients, to calculate the lift-to-drag ratios. This is important because a higher lift-to-drag ratio usually means a more efficient turbine. Now, after numerous testings and simulations, did our seed-inspired turbines perform better? Well, let's see. Now first, for our power yield. Here's a graph that we got from our results. Higher means better, by the way. Huge difference, right? But then, the one on the bottom is actually the power yields from the seed-inspired turbines. Oof, so ours actually performed worse. But how about for the lift-to-drag ratio? The difference is not as big from the power yield graph, and the lift-to-drag ratios are still actually comparable, but the seed-inspired wind turbines still performed worse.
Now, you're probably wondering, since we only got negative results, does that mean our study is a failure? Nah.
Well, actually, in research, results are results, positive or negative. The negative results actually highlight the flaws of your methodology.
For example, in our case, we didn't realize at first that the mass would significantly affect the performance of our blades because the past studies that we looked at didn't do so. But, intuitively, heavier objects require more force to move, which is why our blades performed worse, because it required more torque. Next, during the testings and simulations, we only considered the angle of attack. But, during the drop test, the seeds actually exhibited angles of roll and yaw, which is a rotation from the Y and Z axis. We believe that this actually contributes to the seed's aerodynamics and should be considered in future iterations. And finally, because we were limited by budget and time, we couldn't test our turbines in a wind tunnel, where you can control the wind speeds. But how is this important? Well, a study by Nikhil et al. In 2016 determined that the ideal wind speed for the mahogany seed-inspired turbine, which is also an auto-gyrating seed like ours, was around the same as the velocity of the seed during the drop test. In our case, that would be around 2 to 3 meters per second. We believe that if the mass and the angles were considered, our blades would perform better at those wind speed ranges. To conclude, we found that there's no improvement in the power yield and lift-to-drag ratio of the developed seed-inspired hot blades at the chosen angles of attacks and wind speeds compared to the NACA 4412 control hot blade. However, we also recommend future studies to utilize an optimization method such as central composite design to remove unwanted parts in the model, to consider the angles of roll and yaw, to utilize a wind tunnel for lower wind speed testing, and to use a thinner cross-section for the seed-inspired blades.
That's all, and that's hot.